Hello there, welcome to my channel which offers chemistry lessons mainly focused at the AQA A-level specification but also the Applied Science BTEC chemistry section. So please hit that subscribe button and see how many subscribers we can get to. This video is on AQA A-level video and it's going to focus on an inorganic topic which is group 2. So the specification point is 3.2.2 and it's group 2 and that's classed as an inorganic topic. Now, as always, we start with the specification in front of us and we have a look at the list of things we should be able to do or the things that we should know. Now, one of the issues with inorganic chemistry is it does feel like it's almost a very long list of stuff that you just need to know. And there is truth to that. There is quite a long list of stuff you need to know, but the more sense you can make of it and the more links and trends you can see within that list, the easier it becomes to learn. So we're going to start with the very first point there, which is look at the trends in atomic radius and the trends in first ionization energy. Well, hopefully the radius one is a very straightforward and simple one to explain. So there we've got the group 2 elements, look, from beryllium, magnesium and right the way down to radium. Now the radius, without any exception, the radius increases as you go down the group. And that's simply because you've got more shells. So period 2, we've got 2 shells, period 3, 3 shells, period 4, 4 shells. So the more shells you've got, the bigger the radius. So it's quite simply, as you go down the group, the radius increases. And that is true for every single group. Ionization energy then. Again, this is a trend that you've looked an awful lot at AS chemistry, but the trend as we go down a group, the trend is a decrease in ionization energy. So if we were to show it on the graph, we'll find that we have a decrease and it kind of slopes off, but we don't need to be able to explain that trend. We just need to know that as you go down the group, we have a decrease in first ionization energy. And if we recall the factors that we must consider, we consider the radius, we consider electron shielding, and the third factor is nuclear charge. Now, as we go down the group, the radius increases because there are more shells. The electron shielding also increases because there are more inner shells. The nuclear charge, however, does increase. However, if you remember your argument from first year topics, that these first two factors will outweigh the increase in nuclear charge, and therefore the outer electron is less strongly attracted to the nucleus and has a lower first ionization energy. So as we go down the group, there are no exceptions. As we go down the group, the ionization energy will decrease because we have a bigger radius, we have more electron shielding, despite the fact that there is an increase in nuclear charge. Less energy is needed to remove the outer electron, and the ionization energy will decrease down the group. Now let's have a look at the trends in the melting point as we go down the group. So just a reminder, when you're talking melting point, we're talking about structure and bonding. Okay, so we're identifying the structure and the bonding. Now these are all group 2. They're all metals, so the structure and bonding in all cases is going to be giant metallic, which means that they are held together by strong electrostatic attractions between a regular arrangement of positive metal ions and a sea of delocalized electrons. And in each case, the ions are all going to be 2+ because they're all in group 2. So if I was to draw 6 ions, they'd all be 2+. And I would draw delocalized electrons, and again, if I'm drawing 6, I would need 12 electrons. Okay, I'm going to stop there, but I would have my sea of delocalized electrons, which is free to move, and I can explain why it conducts electricity and why it has a high melting point, because the electrostatic attraction between the sea of delocalized electrons and the regular arrangement of positive metal ions is strong, which requires a lot of energy to overcome. But we're comparing the different strengths as we go down the group. Now, as we go down the group, The only difference is the ions become bigger. If the ions become bigger, they have smaller charge densities because you've got the same charge in a larger volume. So the same charge in a larger volume means a smaller charge density. The charge is less dense. So the metallic bonding in calcium, for example, will be weaker than the metallic bonding in beryllium. So as we go down the group, we expect to see a decrease in melting point, and we do. So beryllium will have the highest melting point and radium will have the lowest melting point. Okay, and the general trend is a steady decrease. Okay, so let me just finish this. 1, 2, 3, 4, 5, and 6. So we do see a steady decrease. We do need to, well, we don't actually, but magnesium doesn't fit that trend, and we don't even need to explain why. Okay, I'm going to leave that out. If you really want to know, you can please comment, and I'm quite happy to follow that up and explain why, but I'm going to avoid that explanation because we don't need it here. We don't need to overcomplicate it. The trend is a decreasing melting point as we go down the group. You can completely ignore the fact that magnesium doesn't fit that trend, and we just need to say that because as we go down the group, the metallic bonding becomes weaker because the ions have a larger ionic radius, they have the same ionic charge, therefore a weaker charge density. You could also say that because they're bigger, they are less compact. So the attraction between the delocalized electrons and the C, the regular arrangement of positive metal ions, is weaker. So the attraction between the electrons and the positive ions is weaker as we go down the group, therefore melting point decreases because less energy is needed to break those bonds. You don't even need to know that magnesium doesn't fit the trend, so let alone having to explain it. Okay, so let's have a little check of where we're up to. We have explained the trends in the radius and ionization energy, and we've looked at the trends in the melting point of the elements in terms of their structure and bonding. Okay, so the next thing we're going to look at is the reactions of the elements magnesium to barium with water. So notice how we don't talk about beryllium, don't talk about radium. So we're just going to focus on these 4 elements and their reaction with water. The reason we don't talk about beryllium is because it doesn't react with water, it's unreactive with water. And we don't talk about radium because it's a very rare element, it's a radioactive element, kind of similar to GCSE when you didn't talk about francium. Okay, and we'll start there actually because in GCSE you looked at the trend in reactivity of group 1 and in particular with water. In fact, you probably observed your teacher dropping group 1 metals in water, and you would have the group 1 metal would react with water and it would form the metal hydroxide. Don't need my brackets there. You would form metal hydroxide and hydrogen gas. You would see effervescence or fizzing. You would see the lithium disappear as it reacted with the water. They were called alkali metals because they would form an alkali here. This is an alkali. And you saw them become more reactive as you went down the group. The effervescence was more violent, the reaction was more violent. In fact, potassium was so violent it set on fire. So reactivity increased down the group when we looked at group 1 at GCSE, and we had to even go a step further and explain that. And we would say that during reactivity, the outer electron is lost, and as we went down the group, the outer electron was further from the nucleus, there was more shielding, it was more easily lost, which meant it was more reactive. So as you went down group 1 metals became more reactive. Now the good news here is when we look at group 2, it is pretty much identical to what we've just talked about there. So this is pretty much your same GCSE explanations here. So the metals, magnesium, calcium, strontium and barium, they will all react with water. And the good news is they will react with water in the exact same way that group 1 does. It makes the metal hydroxide. You just need to be careful here though, because it's group 2, they are 2 plus and hydroxide is 1 minus. and we still make hydrogen gas, so we get effervescence. Check it's balanced. There we go. And that equation is true for magnesium, calcium, strontium and barium. So I could just say barium, 2H2O makes barium hydroxide plus H2O. And I could, H2. And I can put the state symbols in again. And just as you saw in group 1 at GCSE, as you go down the group with group 2, the same scenario, they become more reactive. So the reaction of barium will be a more vigorous reaction than reaction of magnesium with water. And that is because the outer electrons are further from the nucleus. During reactivity, or during this reaction, the electrons are lost, which means if it has a bigger radius and more shielding, the outer electrons are more easily lost, and therefore making barium more reactive. Those electrons are more easily lost in that chemical reaction. So barium is more reactive, and you'll see that trend that calcium is more reactive than magnesium, strontium is more reactive than calcium and magnesium, and barium is the most reactive out of those 4. Now, there's only one extra little annoying thing to look out for here, is that magnesium will react slightly differently with steam or water. Okay, the rest won't. The rest you're going to get the same reaction, but magnesium, if you used steam, and I'm going to show that with the state symbol by showing H2O gas, that's steam, it will actually react slightly differently. And what it makes is, instead of making magnesium hydroxide, it actually makes magnesium oxide and hydrogen. So I don't actually need that 2 to balance the equation this time. You actually make magnesium oxide, hydrogen gas. Okay, we don't need to be able to explain why, but we can if we want to. We don't need to be able to explain why. It's just one of those annoying things that you're just going to have to learn in inorganic chemistry. So my advice would be maybe is to go back through this slide again and get yourself some flashcards, because flashcards are very good at making revision notes for inorganic chemistry. As you'll see as we go down this list now, there are certain things we need to be aware of, such as solubilities and uses in medicines and uses in agriculture. So it's important, I guess, to write notes on these and have these on flashcards and keep them separately. There are some aspects of A-level chemistry that lend themselves to understanding and application, which is the vast majority of it, is particularly in physical chemistry. It's lots of understanding of concepts and applying them in many different ways into the exam questions. But there is quite a lot of your inorganic that you just need to know some stuff. And as I said earlier in this video, be able to explain your trends and understand the trends, that makes it easy rather than memorizing loads. But unfortunately, there is an element of needing to know stuff in this topic as well. And that's one of them, how magnesium reacts differently. Now, I did hint that I'd let you know why. We don't need to know why, but basically what happens is it does form the hydroxide, but due to the high temperature, because it's steam, due to the high temperature, this is unstable at high temperatures. So basically what happens is it decomposes under those conditions. So the magnesium hydroxide is unstable at high temperatures and ends up decomposing to magnesium oxide and water. Don't need to know that bit, but that's the science behind it, okay? Okay, so this is definitely worth making a note of on a flashcard, because this is a rather standalone thing here, is the use of magnesium. So magnesium is a group 2 element basically, and one of its major uses is the extraction of titanium. Titanium is a very useful metal. It's used an awful lot in hospitals and medicines with joint replacements, possibly heard of that. So I think that's why it pops up here, because magnesium is in group 2 and it is used to get titanium. Okay, so I'm going to give you a couple of equations. Now the first one we don't really need to know, but it kind of helps our understanding. So titanium is found, like a lot of metals, in its ore, and one of the main compounds found in titanium ore is titanium oxide, TiO2. Now what happens is this ore is obviously mined, but then it's reacted with chlorine. Now this equation we don't need to know, okay, so we don't need to know this, but like many extractions of metals, carbon is used, and the reason we use the chlorine is to get the TiCl4. That's what we want. So we don't need to know this equation, but this TiCl4, titanium chloride, this is what is used and reacted with magnesium. And this is the equation we do need to know. So TiCl4 is reacted with magnesium metal to form titanium metal and magnesium chloride. So it's kind of a displacement reaction going on here, but we've also got a reduction taking place. Okay, it's a redox reaction. Now, if you haven't done redox yet, which many of my students haven't, then this obviously doesn't make too much sense. It might make sense from GCSE in terms of oxidation and reduction, but this is the main equation we're looking at using magnesium in the extraction of titanium. But it's worth pointing out here that titanium isn't found as TiCl4, it's actually found as titanium oxide, and we need to form TiCl4 first. So that's the process of using magnesium in the extraction of titanium from TiCl4. So you can see there it actually tells you from TiCl4. So the first equation, don't need to make a note of. This is the important one for your notes and your flashcards, that we must know that equation there. The next thing for us to consider then is to look at the relative solubilities of the hydroxides of magnesium to barium, and also at the same time we're going to look at the relative solubilities of the sulfates. Okay, so we're going to do both of these at the same time on this slide. So in terms of the hydroxides, so the group 2 hydroxides, M represents Mg, Ca, Sr or Ba, and the metal 2 sulfates. And again, M represents Mg, Ca, Sr and Ba. As we move down the group, the solubility of the hydroxides increases. So they are increasingly more soluble. Specifically, magnesium is only sparingly soluble. And you'll see that point here. MgOH2 is sparingly soluble. That basically means it's not quite insoluble. It's almost insoluble. It's only a very small, only a small amount will dissolve. So it's sparingly soluble, almost insoluble. And as you go down the group, they become less soluble. So it's the opposite trend. The sulfates become less soluble as you go from magnesium down to barium, and the hydroxides become more soluble. Okay, so make that clear on a couple of revision cards, that the group 2 sulfates become less soluble, and at the bottom, barium sulfate is in fact insoluble. So barium sulfate is insoluble, magnesium sulfate is soluble, and as you go down, they become less soluble to the point where barium is insoluble. And you see that here, look, BaSO4 is insoluble. And when it comes to the hydroxides, they become more soluble down the group, okay? Starting with magnesium, which is sparingly soluble. So not quite insoluble. So make that clear on a couple of revision cards, the solubility of hydroxides and the solubility of sulfates. The final section here for group 2 is to look at the uses of group 2. Now, we saw in an earlier slide the use of magnesium in the extraction of titanium. So there's your use of magnesium right there. Further down, we have the use of MgOH2 in medicine. Now, this is also often called milk of magnesia. So this here is used to treat excess acid in the gut. And the good thing here is because it's sparingly soluble, it doesn't cause any irritation in your gullet when you swallow it. So it's used to neutralize excess stomach acid or excess acid in the gut, which is HCl. And next we have the use of CaOH here in agriculture, and there's no equations for this one. It's just we need to know that this is a base, and when dissolved in water it will form an alkali. So what it does is it increases the pH of soil. So if you have slightly acidic soil, you can add slaked lime, which contains calcium hydroxide, and what that does is it increases the pH and improves crop yield and growth of certain plants in agriculture. Moving on, we've now got two equations here, and two equations for this one are the use of CaO or CaCO3, there's CaO, CaCO3, they are used to remove SO2 from flue gases. Now what this means is sulfur dioxide is quite often a pollutant, or sulfur is a pollutant in fossil fuels. You may remember that from GCSE, that fossil fuels can contain sulfur, and therefore when you burn the fossil fuel in industry, you're also burning the sulfur, which creates SO2 as a pollutant, and instead of releasing it into the atmosphere, the SO2 is removed from these flue gases using calcium oxide, calcium carbonate, and there's two equations there to show that happening. Moving on, the use of BaSO4 in medicine. So this is often referred to as a barium meal, which a patient can drink before an X-ray, and it allows the doctors to take a photograph or an X-ray, if you like, because BaSO4 being insoluble, it will block X-rays. So this BaSO4 actually blocks X-rays, and as you can see on these images here, this patient has drank a barium meal, and the doctor is able to take X-rays at specific times, and they can see the movement of this barium sulfate through the gut. So it basically allows them to take pictures of the outline of the gut and to identify any issues there. So that's a barium meal. Now, one question you often get asked here is the fact that barium itself is actually highly toxic. So why is it that doctors can give you barium sulfate to drink despite the fact that barium is highly toxic? And the reason for this is because barium sulfate is insoluble, therefore barium is not absorbed into the gut. So it's not absorbed because it's insoluble. Moving on, it says here the use of acidified BaCl2 to test for sulfate ions. You actually saw this at GCSE, that you use barium ions to test for sulfate ions, and you get a nice white precipitate of barium sulfate. So you get a nice precipitate of barium sulfate. That's showing that barium can be used to test for sulfate, because if the sulfate ions present, you will form a white precipitate. And it says here the use of acidified. It does need to be acidified, so you need to add acid to it, because the acid will remove any impurities that may also form a precipitate with barium. So that's to remove the impurities. Okay. Now, I suggested in earlier slides that you need to make yourself some flashcards or revision cards. I'm not a great fan of revision cards for A-level chemistry. However, specific topics do really lend themselves to it, and this is one of them. So writing down the uses, having these equations on revision cards, and likewise your trends in your solubility, your trends in radius, trends in ionization energy. It's nice to have it all in a few revision cards to summarize it. Okay. Right, well, that's the end of group 2. Hopefully that was useful. Again, please let me know if there's anything that you're unsure of, or if there's any more help you would need. Thank you.